So what we see here is, of course, geometric progression. So it's t log 1 minus e to the power mu minus epsilon k over temperature, right? On omega k is equal to minus t logarithm 1 minus e to the power mu minus epsilon k. So this is a reflection of fact that the bosons can occupy given quantum state with arbitrary quantum numbers. Okay, let's define the distribution function for average number of the particles in the given state k, which again using your knowledge of statistical physics, it's a derivative of thermodynamic potential omega with respect to chemical potential. Something is wrong here, and you didn't correct me that when I define omega, there should be minus here, there should be minus here, there should be minus here, and in total sign plus here. Because we define the thermodynamic potential omega, which is PV, by the way, as minus t logarithm of the partition. Okay, let's take a derivative for bosons. You have mk average is equal to e to the power epsilon k minus mu over temperature minus 1. And this is Bose-Einstein distribution function. Let's make one comment. Suppose that this exponent is very large. Then, if e to the power mu minus epsilon k over temperature is much smaller than 1, it means that e to the power epsilon k minus mu over temperature is much bigger than 1. So this is equivalent. Then mk average is approximately equal to e to the power mu minus epsilon k over temperature. And you see from here that this is much smaller than 1. So if the occupation numbers, average occupation numbers are very small, we are back to Boltzmann statistics, which is a limiting case of Bose-Einstein statistic if the occupation numbers are very small. Of course, if we know that, we can write the total energy. It's sum over k epsilon k and k. So if we know the distribution function, so we know all thermodynamics, we know everything. But let's look at this expression a bit more carefully. We said that the occupation numbers are arbitrarily large, and in order to have average occupation number positively defined quantity, which is true, we can not have negative occupation number. First of all, we see the conclusion that mu should be non-positive. Why? Because we have to have this quantity bigger than 1. And epsilon k is positively defined quantity, it's k squared over 2. So if we now draw the chemical potential as a function of temperature, and we use this consistence with Boltzmann statistics. So it's chemical potential as a function of temperature. So somewhere here it's large and negative, as it should be for Boltzmann statistics. You remember that for Boltzmann we have a distribution nk is equal to constant times e to the power minus epsilon k over temperature. And this one depending on chemical potential. So chemical potential is some logarithm over temperature. But what can happen that at some point chemical potential is equal to 0. Suppose that, of course, it's a smooth function. It should not have any kink. What happens if the chemical potential is equal to 0? Then formally you see that we are in trouble, actually, because this average number of particles occupying the state with a k equal to 0 diverges. Because if k is equal to 0, epsilon k is equal to 0, mu is equal to 0, exponent is equal to 1, 1 minus 1 is eliminated is equal to 0, and we divide 1 by 0, and we have infinity. And this is actually a reflection of the fact that for temperatures below critical temperature, which we easily obtain calculating thermodynamics of quasi gas, the bosons start to accumulate in the lowest quantum state. So it will be macroscopic number of bosons sitting in the state characterized by low energy. Why I'm saying low energy? Because in order to characterize energies of that sort, I adopted, of course, the concept of box. So we have three-dimensional quantum well of the size Lx, Ly, Lz, and these particles are not feeling any kind of external potential. This is external potential where in which particles are sitting, so the hard walls means that the particles cannot escape from the box. However, and we discuss in experiments to trap bosons in the trap, people use magneto-optic trap, therefore the particles are sitting in some potential, and you see that in parabolic potential, as you know, the lowest state is here, therefore bosons will be accumulated not at zero energy, but at lowest possible energy in given potential. So at critical temperatures, particles start to be accumulated in this state, and at zero temperature, all particles, provided that they are not interacting, are sitting in the lowest possible energy state. So here we have phenomena known as Bose-Einstein condensation. And you see that the possibility to condense of this state just follows from the fact that the quantum numbers can be arbitrary for a system of non-interacting bosons. Of course, the question is how different interacting bosons are from non-interacting bosons, and this was actually one of the key questions why the Bose-Einstein condensation was not observed in the system for nearly 70 years or 80 years, no, probably 60 years. While it was discovered in 1924 and has not been seen at all. And the reason was that the most prominent candidate for this condensation that time was helium, and helium is interacting system. So the effects of interaction or many body effects prevent system to sit in the condensate, so interaction is important. And only in middle of 80s, people doing quantum optics discovered that the gases of alkali metals being put in magnetic optical trap can Bose condense, and they observed this Bose-Einstein condensation using time of flight experiments. And the reason that very big fraction, 99.99% of particles were in the condensate was that they are not interaction. So, message, effects of interactions are important, but if they are small, system collapse in Bose-Einstein condensate state, which we discuss in more details probably next week. Questions? If not, I will discuss fermionic systems on the same footing. Okay. Let's now consider fermions. So, omega k is equal to minus p logarithm sum over nk e to the power mu minus epsilon k over t to the power nk. But for fermions, we know that nk can take only two values, 0 and 1. Point. And this is a Pauli principle. Therefore, instead of having geometric progression like for bosons, we have only two terms, minus t log 1 plus exponent to the power mu minus epsilon k over temperature. Compare this with that. Okay. The distribution function nk, which is minus d omega over d mu, is equal to 1 over e to the power epsilon k minus mu over temperature plus 1. Again, so with this formula, we don't have to say anymore that chemical potential is negative or non-positive. It's rather other way around. What shall we do? Let's plot this function first at 0 temperature. So we see at 0 temperature, we start to fill states with given k, and each state can be occupied by one particle with a given projection of spin. We know that fermions are particles characterized by half integer spin. In the most simple case, when we are talking about electrons, we have spin 1/2. Therefore, if we look at quantum well again, so we have some levels which are not equidistant. So we put one particle with given projection of spin at each level, and therefore we fill all states up to energy mu. So nk is equal to 1 up to energy mu, and then equal to 0. Okay? So what happens if the final temperature is considered? Then this function is smeared. So this is final temperature distribution function, which you can plot yourself using this formula. But the point is that the energy which separates filled states and empty states, because here the states are empty, at zero temperature is a chemical potential, is a Fermi energy. So Fermi energy is a chemical potential at zero temperature. So we define the energy which separates occupied and empty states, and we call this energy Fermi energy. If I add the total number of particles is of course sum of the K and K average. Okay, I hope you know that, but now we will do simple calculation in the remaining, say, 10 or so minutes. We will do simple calculation which will allow us to connect the number of particles in this fermionic system with the Fermi energy. Okay. Once again, I'm emphasizing the difference. Here, the Fermi energy or chemical potential at zero temperature is entirely positive and large number. Here, for bosons, the chemical potential is not positive. However, if we look at the same limit, namely, if the occupation number is very small, namely, if this exponent is much larger than 1, what can we see? That the same limit, namely, let me write, if nk average is much smaller than 1, nk average is equal to e to the power mu minus epsilon k over temperature. So we have the same limit of Boltzmann statistics, which is originating from Fermi statistics, the same way as it derived, it appeared from Bose statistics. So this distribution function, if I forgot to mention, is known as a Fermi Dirac. And Boltzmann statistics is a classical limiting statistics both for fermions and bosons. Good. Questions? Because the last calculation I will do today is calculation relating the number of particles in the system with Fermi energy. First of all, let's define the Fermi momentum such a way that mu, which is its Fermi energy, mu at temperature equal to 0, is h bar square, k square over 2m. So I just used the definition of the Fermi momentum through the Fermi energy. M is the mass of electron. We suppose that we have electrons, and here I put h bar explicitly. Or you remember agreement that P is hk, so this is Pf squared over 2m. Therefore, Fermi momentum is equal to square root over 2m mu. And this picture, this one or this one, means that if we come to the momentum space and we start to fill in states in the momentum space, we have the surface which separates empty and filled states, and this is sphere. So all states below this surface are filled in, while all states above this surface are empty. So, using this formula, and everywhere I want to do zero temperature calculations, I have n is equal to sum over k over 1. So this is 1 if our k is smaller or equal Fermi momentum. And now I have to recall the fact that I'm calculating the number of particles not for given per projection, but total number of particles. So I have to make summation over spin, which gives me 2 possible projections. So therefore I put 2. Okay. So this is n is equal to 2 times volume. Now I come from summation to integration. Integral dp over 2 pi h cube. And here I have a theta function over mu minus p squared over 2m, which tells me that I'm sitting within sphere. So again, I recall you the convention that sum over k is replaced by volume times integral dp over 2 pi h cube. P is h bar k. Okay, so what I have to do is just to come to spherical coordinate system. Let me write it as an n over volume. Sorry, this is the density of particles. Is equal to what? Is equal to 2 pi, 2. Then, in a spherical coordinate system, I see that nothing depends on angles. So therefore, I have solid angle 4 pi. Here, I have integral from 0 to pf. And here, it's p squared dp over 8 pi cube h bar cube. So 8 is cancelled. I have 1 over pi square h bar cube. And what remains is to calculate the integral p square dp. And we know that this is pf over 3. Good. So, with a simple calculation, we arrived in very important conclusion which connects us the number, the density of particles in the fermionic system with a momentum separating empty and occupied states. Namely, what I have here, I have p f cube is equal to 3 pi square h cube. If you like, it's a definition of connection, definition of Fermi momentum through the density of electrons in your system. This was calculated for a 3-dimensional case. My exercise for you, which I'm not going to include in homework, just for the sake of be sure that you understand everything. Suppose you have two-dimensional layer of electrons, 3 electrons. So you are not in a bulk piece of metal, but you are not a layer of electrons. This is actually what is usually used as electronic device in nanophysics, two-dimensional electron gas. Calculate for two-dimensional electron gas how the density of electrons is connected with Fermi moment. Of course, we can write now Fermi energy. Fermi energy is 1/2m, and we have to write 3 pi square h cubed n over v to the power 2/3. So Pf and Fermi energy. So what we see here, that chemical potential at 0 temperature of Fermi energy is proportional to the power of density, which is 2/3. Density to the power 2/3. As I said, the reason which we started with 0 temperature calculation is that all difference of final temperature compared to 0 temperature is smearing out of the distribution function. And this smearing out appears only in the region which itself is proportional to temperature. As you, I think, heard many times in solid state physics course, we are dealing with bulk systems, which are metals or gases or whatever, which consists of macroscopic number of particles. So the number of particles in this piece of chalk is 10 to the power 23, 10 to the power 24, which is a huge number. If you plug in this density, and again, do this exercise to calculate what's the typical values of Fermi momentum in metal, using the density 10 to the power 23, you will get some number. Do this calculation. Number. We discuss it. We discuss it later. But if you plug it into the energy and calculate the typical energy, it will be of the order of 10 electron volts, which is 10 to the 4, 10 to the 5 kelvins. While at room temperature, we have 300 kelvins. So room temperature, as I said, is 300 kelvins, while typical Fermi energies is 10 to the 4, 10 to the 5 kelvins. So you see that effects of temperature are of the scale 10 to the power minus 2. And even at room temperature, for typical metals, we don't have to care about temperature at all. And therefore, we can say that we are at 0 temperature. And only when we are looking for temperature corrections, which we, by the way, learn are all of the order T over Fermi energy square. This is how corrections to thermodynamic potential appear. So you see that these corrections are far beyond the accuracy of 1%. And only when we need a temperature dependencies for the Fermi systems, we will take these corrections. Yeah, that's probably all. Summarizing, we discussed symmetries, and from symmetry reasons, we arrived at conclusion about behavior of wave function, many wave function of non-interacting particles. And we learned that wave function is either symmetric, and then we are dealing with bosons, or antisymmetric, then we are dealing with fermions. Then for bosons, we calculated a distribution function and have seen the possibility of boson state condensation, while for fermions, we calculated distribution function and arrived at the concept of Fermi surface and Fermi energy. This was done, as I said, for non-interacting fermions and bosons. And one of the objectives of this course is to see what the effects of interaction bring to us, or what can we say about system of interacting fermions and bosons, what are the approximations which we can adopt to discuss interacting fermions and bosons, and when this approximation is good and when it is not. Okay, questions? If not, please, next time, don't be late. We have very many things to discuss. And if you have any questions or misunderstanding of what has been said, send me email or come to my office. Until Wednesday. Well, if you request that, I will come to Patrizia and arrange it to make it official. I mean that everybody knows that this is, for me, it's the same. I mean, we can start at 9:15. Of course, we are 9:10.
Just a suggestion. Generally, half of us take 40 bus, which means something 5 minutes late.
Look, discuss it among yourselves. I am not against this. So if you come to agreement that majority wants it, come to Patrizia and we shift it. But please let me know that for me there is no difference. Good.
My intention is opposite direction. My intention is to start at 9. But I'm not going to say anything. I don't have any problem. Yeah, I don't have any problem. I understand. Today I was also rushing to it. So I don't have any problem. You can shift me. Yeah, you can.
Don't, I will not let you to sit in my class. If you are, if you are exceptionally late, if you have some exceptional problem, you are late by 5 minutes, not always. Okay. It can be accommodated. But if you are late more than 5 minutes, that's why. take a bus at 8:20. Okay, I woke up and listen, we managed. Everybody was very punctual, and but like Nora and I was rushing to catch the 8:20 bus, but unfortunately we missed it, and it's definitely we are going to be late. That's why I put a request, but I was so strange. I had a so strange response from people that no one was happy with it.
But most of the time, all of us come with the 8:40 bus.
But nobody said it's okay.
I didn't know anything. Now
No, I don't. No, Yasin said no.
Yasin is always, I don't know, maybe he comes soon, but what about the others?
But even from the others, nobody said okay. We should. Like I just looked back and I was.
I haven't tried always to take 8:20 bus.
But you have if we don't agree together to ask him to start always the class at like we had this setting in Friday meetings that they start at 2:10 for prayers.
Yes,
So
10 is not so.
and we have a reasonable, we have a very good reason that the bus leaves at 8:40. We can start 9:10, finish at 10:40.
If he's so sensitive to the time, I think he should do that.
No, he is very strict. That's why I don't have any problem. But when he was so strict, that's why I said
You know? Let's go out because everything's recorded.
Who's this?
Uh,
Who's this? Is yours?